All right, then we have lesson 10, part 2. That is a magnetic moment. All right, so we'll have a magnetic moment sitting out here. It'll have some angle to a magnetic field. This will be a magnetic moment, small m. And our magnetic field will look something like this. Right, we'll have it, I'll write this uniform, but we'll have to do some interesting things because of stuff, because we'll talk about that in a moment. So this angle between this line and there is theta, so that's the angle between those two guys. So what we want to do is we want to know what the force is there. And the answer is there's no force. Just like with the electric dipole moment, the magnetic moment feels no force. So if you put your permanent magnet in a uniform magnetic field, then it will just sit there, okay? Because, remember, we can pretend like this is two charged objects there, right? So the force from this one is going to equal the force from that one, but be in the opposite direction because it's also from the force field. So the force here, the force there will cancel, so it'll just sit there, almost. Because around this, you see that this is going to be pulling it, I hope that's counterclockwise for you, and this is going to be pulling it counterclockwise as well, so it's going to make it spin, right? It's going to make the object here try to align with the field. So magnetic moments naturally try to align with the magnetic fields, all right? So that's the effect of a uniform magnetic field, is alignment. So that gives us part 2. A magnetic moment feels no field. Or feels no force. From a uniform, and only a uniform, and A is, oops, but it feels a torque. Okay, so that torque is tending to make this align is then going to be the magnetic moment, M, this guy, times the magnetic field, B, this guy, times the sine of theta, once again, between these two things. See a lot of those sine thetas running around. This has, again, a right-hand rule, unfortunately, because the torque has a direction. And that right-hand rule is, let's see, I think this is the right hand. M, and then B is the middle finger again, and then the torque is this one. All right, so we have right-hand rule, I think the last one was 2. So this is right-hand rule 3. The index finger is the moment, magnetic moment. And the, what is it, middle finger is the field, and the thumb is the torque. Okay, so that's what we've got for getting the direction. So in this case, M is this way, B is that way, torque is this way. Coming out of the, or yes, out of your board, hopefully. Okay, so what do we do here? So we've got this, but we do want to talk about how these things interact with a force. So this might seem a little bit like you've heard it before, and you have, because it does feel a force from non-uniform fields. Yeah. Okay, so what does that mean? That means that, again, if the field is different here and here, right, then the force from this one and this one are different, and then you feel a force. So in the example, I'll take a non-uniform field with an electron, and I'll show you what the force on that electron in a non-uniform field is. How does this look? Well, that force is equal to Qm times the B in the positive part, and then Qm minus Qm times B in the negative part, so positive and negative here. We're going to pretend they're always going to be collinear. It's technically true that they could be different. Now, I do want to warn you here that you want these positions to be as small as you can make them. Now, you get to make them however much you want, however close you want, but as you change that, as you recall, the magnetic moment dipole approximation is QMD, right? So this is your magnetic charge, your imaginary magnetic charge, times the distance here, right, D. So it's best to try to get these nice and close, but as you do that, your imaginary charge is going to decrease. So you'll have to make that sort of trade-off when you do any problems like that. And you want that as close as you can make it, right? But you might have some numerical problems if you try to make them too close. So less than 10% is probably a good D, I think. We'll look at that a little bit in the example, all right? So that's what happens with this guy. The magnetic field tends to align magnetic moments to it. That's the most important thing. And that actually is very important for, let's say, a compass. If this was a compass needle, I should have done a compass example. If this was a compass needle, this thing would try to align with magnetic north. And then you can find your way around in the wilderness, right? Stuff like that. Very interesting. So that is the force on a magnetic moment from a magnetic field. Next, I'll talk about the force on a section of wire from a magnetic field. A long, straight section of wire is all I'll care about for this. So we'll talk about that next time. All right? Bye now.